All right, let's see. We're going to talk about a whole bunch of software that we've been developing over the last probably 2 years, 2.5 years, to enable communication for the new Intel Xeon Phi card. So this all started, a couple years ago, 2.5 years ago, when Bill Magro came to me and he said, Intel's going to build one of these accelerator cards, kind of like the NVIDIA guys are doing. And sure, we can do the same style of programming, the offload compiler type technology where you offload a subroutine into the box, you copy the data over, you copy the code over, you copy the results back. And I said, oh yeah, sure, we can do that. We invented that at Floating Point Systems in the late 70s, early 80s. But Bill Magro, being the application guy that he is, he said, well, but the application programmers, they would rather prefer, if they didn't have to use this special technique of programming, they would rather just run the MPI ranks on the card and just use their MPI jobs the way that they do today. And so we had a brainstorming session, and he said, well, what could we do? What might be possible so that we could enable MPI applications, the ranks, to actually run on the card and access the InfiniBand network. And we came up with a few ideas. We said, well, we had some technology that we had on the shelf that I'll talk about. It was at the time it was called the Direct Ethernet technology that we actually implemented a software-based RDMA over a UDP kind of queue pair. And I said, well, we could take that technology and we could use it for communicating inside the box from the card to the back to the host, but using RDMA interfaces. That gets us the ability then to run MPIs that are already coded to use the Open Fabrics interfaces, within the box between the cards and the Xeon. And he said, well, what could we do though to actually have the MPI ranks be able to actually access the InfiniBand device directly? And so we did a lot of brainstorming there, and that'll be the second topic I talk about, which is this Direct HCA access from the Xeon Phi. And to do that, we had to invent a whole bunch of software magic because the card itself is a PCI card, and you can't dedicate a NIC device to a PCI card that doesn't have a PCI root complex. So how can you actually have cards directly DMA data between themselves? And I'll talk about how we did that with PCIe peer-to-peer transfers and a whole bunch of software to make that happen. And then the third thing I'll talk about is a piece of software that we developed late in the project, which was to increase the ability to get higher bandwidth from the card to the network, actually going through the host. And I won't call this a workaround to a hardware bottleneck. I'll call this a way to optimize the software to get the best performance out of the platform. Notice how I didn't say a workaround. Okay, and then I'll talk a little about the software, where to get it, and this new version of a branch release of OFED that we've just released today. Okay, let's see here. Okay, so getting back to a software-based RDMA implementation that allows communication within one Xeon to Xeon Phi cards that are in that platform. So that's fairly straightforward to do. One just writes a hardware-specific driver. In this case, we call it IBSCIF. It plugs into the core layer and it says, I'm a hardware device. I know how to do RDMA. And then a user space library. And then instead of going to an InfiniBand or IWarp device, we have a low-level driver that was developed for the Xeon Phi card for allowing communication between the host and the Xeon Phi card, or between Xeon Phi cards within one platform. It's called SCIF. And so we just implemented the queue-pair-based semantics of RDMA and software in the IBSCIF driver, and used this low-level driver that allows basic, DMAs back and forth from the host to the card between cards. And then with that, then we can run the MPI on top of that, either directly down through the Open Fabrics verbs or through uDAPL. And again, the reason why we wanted to do this is we wanted to provide, standard interfaces for communication. We invented this new SCIF library. We could go out to the world and say, oh, well, just recode your MPI to use these new, this new communication facility. But we realize that the Linux RDMA stack is a standard. Some people say, well, OpenFabrics doesn't develop standards; they follow standards. But I would propose that we do develop standards. The APIs are really a standard. Okay, the RDMA APIs. And so, as I mentioned, it allows communication between the host and the cards. Plugs into the core layer. It does emulate, the RDMA semantics in software. And because of that, it actually has higher latencies than one would have going to a hardware-based InfiniBand device, which is actually doing kernel bypass. The IB SCIF driver actually has to go to the kernel for all this activity. It has to emulate the software-based queues, which adds latency. But when we get to the the large messages, we actually get pretty good bandwidth with this. So that got us, communication within a box, and we could run MPI unmodified within the box and run MPI ranks on the Xeon Phi cards, or some on the card, some on the Xeon. Then we started brainstorming about, okay, well now how are we going to be able to do, or could we be able to do, direct access to an InfiniBand HCA? So we had several meetings with our PCI architects and said, well, what are the capabilities that the card has, and could we do this? And they said, well, the card actually does, and PCIe has a semantic called peer-to-peer transactions that if you set things up correctly, you can actually DMA directly from any PCI card to another PCI card. Or I'm sorry, from a PCI card to another PCI card or to the host using the peer-to-peer transaction. So we started looking at how we might do this. And the whole goal, of course, is to make this accelerator, this strange-looking thing, look more like a normal computer where we just run MPI jobs on all the nodes, on all the KNC cards, and they can all talk across InfiniBand with MPI ranks. Okay. So the hardware magic that makes this work starts with some capabilities that are on the Xeon Phi card. And they have several sets of registers that allow aperture windows. So these aperture windows allow you to map host address space into the address space of the Xeon Phi card, or Xeon Phi address space into the addresses of the host. So what we decided that we could do would be map the HCA's register sets, the doorbell sets in the HCA and the bar space, PCI bar space, into the Xeon Phi address space. That would allow it to directly access the hardware without having to go back to the host. Similarly, we can map the memory space of the Xeon Phi card. Each one's got like 16 gigabytes into the address space of the host. Okay, and so by doing this, we could then develop software that would allow us to map these register sets into process address spaces on the Xeon Phi card, and then they could access the hardware directly. We could write software that would allow us to, when we register memory, we have the Wookiees that point to the data, we register the memory, we could register it back with the HCA such that the HCA is seeing the memory that's in the address space of the host, so it thinks it's dealing with a host address, but really that memory is on the Xeon Phi card. So that's kind of the hardware that makes the magic work. Now, the rest of it was just a mere matter of programming. So Bill said, go do that, Woody. I said, okay, well, come back in a year and check on us and see how we're doing. So we spent, a year and a half or so writing software. And so what we decided to do was we
had another hardware-specific driver, this vendor proxy driver, and it plugs into the core layer, and it says, hey, core layer, guess what? I'm an MLX4 card, or I'm a QIB card, or I'm a NetFX card. In our case, we started with the Mellanox MLX4 card. So the IB core on the card thinks it's dealing with an HCA. It thinks it owns an HCA. Okay, and then it talks to a proxy client. So we have to have, because what we're essentially doing here is we're sharing the HCA, the RDMA device, with the host. The host driver over here actually really owns those resources, right? And so for things like the privilege operations, like, okay, I want to allocate a queue pair, for example. So we come down here, come down through uDAPL or through the verbs library. It says, I want to allocate a queue pair. I opened up the Mellanox device. It comes down through here and he says, I want to allocate a queue pair. The core says, okay, allocate me a queue pair, Mr. MLX4 driver. And what this guy does is he talks across this proxy client over to the proxy server and daemon, which then goes down to the real IB core and to the real Mellanox driver, says, hey, allocate me a queue pair. Mellanox driver says, sure. Here's a queue pair. Now this driver says, okay, but instead of mapping that into the host process address space like you would do normally, we use some other functions in this low-level SCIF driver to map those queue pair register sets into the address space back here on the card. Okay, so now we've got things set up so that the queue pair space and doorbell space is allocated directly into the user KNC process address space. Same thing goes for other privileged operations like registering memory. I have some memory. I come down to the core layer. I'd say registers this memory, goes to the vendor proxy driver, goes over through this client over here. We do a whole bunch of memory mapping magic in terms of converting address spaces so we can find exactly where the memory is now in the system address space of the host, which has been mapped through the aperture windows, and it registers that with the HCA. And then after that, all the speed path operations that are done by the MPI library, posting of work requests or pulling for completions, are actually done directly from the card. Okay. So we've got this vendor proxy driver. So for every different kind of HCA, a different vendor proxy driver has to be implemented that presents itself like the native hardware device. In our case, we had done one for the MT-HCA. We did one for the MLX4 driver. We started on one for the NetFX, or not NetFX, but the Intel iWarp one. So it is possible for iWarp type of devices as well, but decided not to productize that one because nobody really wanted to use that in this environment at this time. And then we had the client proxy driver, which proxies the privileged operations back to the host for allocating queue pairs, registering memory, et cetera. And then the daemon, the corresponding daemon on the host. And then all the rest of the software is essentially unmodified software from OpenFabrics, so the core layer I think we did make a couple small changes in the core, but the verbs library, the MLX4 user space library is unmodified code, absolutely. So we've kind of hidden it all within this proxying infrastructure. Okay, as I already mentioned, once the queue pairs are allocated, all of the interaction with the HC is directly from the KNC. And then the actual data transfers end up getting done using PCIe peer-to-peer transactions. So when we hit the doorbell and we say, Mr. HCA, go ahead and do this DMA transfer, it actually does that using peer-to-peer PCI transactions because it knows that it's a peer device that it's talking to. It's part of the PCI standard. We do have to proxy the completion interrupts back from the host. So the host, again, only actually owns the device. So when an interrupt comes in, if you actually have to ask for a and interrupt for completion. MPI, for example, doesn't. It pulls on memory or pulls on the CQ most of the time. But that goes back to the host, and then we have to send it from the proxy back to the proxy on the, or the client on the CAN-C card on the Xeon Phi. But that does add latency for interrupt. So interrupt-based driven applications might not perform as well in this environment. Currently, the other limitations is right now we started off with just supporting user space clients primarily to support MPI. So we don't have support for all of the OFA core services. We don't have any of the MAD services or SA kind of services at the moment, or RDMA CM. At least for MPI, we didn't need RDMA CM. Most MPI implementations either use sockets or other techniques for doing that at the moment. We are starting to do some research on, if we could extend it to add these additional things. I mean, I don't think there's probably never going to be a reason to run, for example, the OpenSM on the Xeon Phi card, right? So we probably won't ever do that, or the MAT services that it needs. But some of the other things like RDMA CM and SA we probably will do. And we found that this path provides really good low latency access to the InfiniBand network. Now, let's see. Okay, so similarly to what we did for the Mellanox device, where we have the hardware magic of mapping register sets around, we've done a similar thing for the Intel TrueScale card, but the best performing interfaces to get to the TrueScale card's hardware is through the PSM interface rather than through verbs. So we worked with the TrueScale team, and they implemented essentially the exact same infrastructure that I talked about before with respect to having a proxy, a driver, a client, and a daemon running on the Xeon, and it does the same thing where it maps the hardware context into the address space of the card. But then instead of going through the verbs or DAPL to get to the hardware, it goes through the PSM interfaces. So again, an identical idea of using the peer-to-peer software. One thing that we did find that was interesting on the Xeon Phi is when we started getting numbers, people were asking, well, why aren't you getting as good of numbers for things like latency as we do on the Xeon? They're pretty good, but they're not as good as the Xeon. Well, it turns out that code path matters, okay? The Xeon Phi, the cores on there are little. They've got big vector units, but the serial, the scalar performance is not as good. Right? So even though, for example, on a Mellanox card where the hardware is mapped into user space and we're able to access the hardware directly from user space, we're still going through that user space library code path. And it turns out, and we're going through MPI, and MPI is not very well matched to the InfiniBand verbs. So there's actually a lot of code that we have to go through MPI, through the verbs, even in user space to get to the hardware. And on a Xeon, we are spoiled. The processor is so fast on a Xeon, it totally hides all this inefficient coding that we've been doing over the years, to get to the hardware. But on the Xeon Phi, we actually see it. So we see increased latencies, that we do on the Xeon. But we do see also that, interestingly enough, that going through the PSM interface, which is a tag matching interface, which has a impedance match, it matches a lot closer to the semantics that MPI needs. Its code path is smaller, and we actually get better latency. So that's and I think as Bill mentioned earlier, as the fabrics get faster, but the cores are not really getting faster, there's just going to be more of them. The amount of code that we do between, where we hit go through the runtime to the hardware, we have to pay attention to that code path as we move to exascale. So again, this is just a recap of the QIB TrueScale proxying infrastructure. Okay, so the last thing I'll talk about is not a workaround. The last thing I'll talk about is how to get the best bandwidth out of the platform. So as it turns out, in some platforms, this peer-to-peer type of transaction is not as optimized as regular PCIe DMAs. So there are some limits to the bandwidth. And I think we were living on some platforms to around a gigabyte a second, when on a host Xeon to Xeon, we can get unidirectional 6 gigabytes a second with an FDR card, or say 3 gigabytes a second with a QDR card. As it turns out, the performance, though, of using the DMA across that SCIF interface is actually really high. The DMA interface from the Xeon back to the InfiniBand device is really high. So what we decided to implement is a proxying mechanism, so that what we do is that we did this in the context of a uDAPL provider as opposed to at the OFL level, and there was actually architectural reasons why we had to do that there to implement this proxying technique. But what happens is that the uDAPL provider client over on the Xeon Phi card uses this low-level SCIF driver and copies the data, pipelines it over to this daemon process running on the host, and then it pipelines it out the HCA to the destination on the other end. And with that technique, we've seen, well, we're not getting 6 gigabytes a second, but I think, in the lab we're getting, with MPI, 4 to a little 4.5 gigabytes a second. Okay, so now, the direct mechanism that I talked about, the peer-to-peer transaction, does give us good latency, right? And now we have a path that gives us high bandwidth, okay? So we went and talked to our MPI team and said, here's all these speeds and feeds that you can get. You can use this provider, you can get low latency. You can use this provider, you can get high bandwidth. So they implemented a multiple DAPL provider support in the MPI library. It's almost like a dual rail, but what it does is it looks at the size of packets and says, oh, this is a small packet. So it opens up 2 different DAPL providers, one that uses the proxy technique, the other that uses the direct technique, and says, if it's a small message, I'll send it out the direct path right to the HCA, because I know that's the lowest latency. And then at a certain cutoff point where that runs out of bandwidth, I'll use the other provider, so that the MPI application then just sees, oh, I'm getting pretty good latency and pretty good bandwidth out of this, and without having to have the MPI programmer worry about it. Okay. Before I talk about where to get the software, I'll talk just a couple bits about kind of next steps. As I mentioned, currently we started with only implementing user space access, and that was primarily to support MPI. And of course, the first thing we did is that we provided people with, hey, you can run your MPI ranks now on the card. You can run a native application just like you would on your Xeon. They said, that's great. How do I get to my cluster file system, right? How do I get to my Lustre file system? Or oh boy, it sure would be nice to be able to just use IP over IB to configure these cards into my IP over IB back subnet, because I don't want to have Ethernet on every node. So we are investigating that. Hopefully we'll get that done too. But for now, that's not in there. But so I'll tell you where to get the software that we have so far. So we first started with a base, an OFED 1541 base, because OFED 3.5 wasn't out at the time. What we decided to do was, for expediency's sake, was to just ship the software with our mic card platform software stack. So there's this stack that they provide that includes the micro OS for the Xeon Phi card, contains its low-level drivers, the SCIF drivers, and a whole bunch of other software that's shipped with the card. All that software is, or most of it anyway, is all open source, and all the source code is shipped with it. What we did is we took some of the RPMs that we needed to make our changes to. Primarily, it is the OFED kernel RPM, and we added these additional proxy drivers and IB skiff, and we ship it as a kind of an add-on or overlay to the existing OFED 1541 package. So the way people would install this is they would go to the Open Fabrics, get OFED 1541, install it, uninstall the kernel RPM that comes with OFED 1541, and install our version that has these additional packages. Got it, I'm almost there. And this is where you can get that software, and that's shipping today. Then OFED 3.5 was released a month or so back, and people are also asking for support for the Xeon Phi with that. And I don't know if everyone remembers, but our discussion last year with respect to OFED, we decided that for the longest time we were adding in a whole bunch of new stuff into Open Fabrics OFED that wasn't upstream yet, and we didn't want to do that anymore. So we decided we would base OFED on the current upstream kernel plus the user space packages that are currently released, and that's what we would use for OFED. But we also said, but there was some benefit in putting new things into OFED for people to use as experimental or before it was upstream, so we get feedback on it. So we came up with the concept of being able to have a branch release to do those kind of things. And so we've done this for the mic card for the Xeon Phi, and we've created an OFED 3.5 mic branch release. We've just started under development. We actually just today posted a first alpha package. This is where you can get it from the Open Fabrics website. It's a technology preview, which we'll continue to harden here, and then release it as GA hopefully within a month or two. So that's all I had. Questions?
Thank you. Thank you.
Yep.
Any questions?
What? There was one over there.
Okay. Thanks.
Have you made any attempt to push this upstream yet?
We haven't yet. Part of it is because we're not quite ready with all of the code. It's all open source. Some of our lowest level skiff driver, when it was originally written, they decided to take the position of developing software so it could be portable between Windows and Linux. And some of our Linux people looked at that code and said, oh, if you're going to upstream this, you have to rewrite that part, right? So they're kind of off doing that. We eventually want to engage with the upstream people, and so that's probably the last thing that we're waiting for before we could at least start the discussion with Roland and folks.
So you're looking 3-4 months? Is there any time frame? Just I'm wondering how long I have to prepare for this.
I think it's going to be a while. We're still having those discussions actually between my team and the VPG team in Intel that own that driver. But I think they're going to start some discussions within a month or two. I expect that it's going to be a fairly long time. I bet it's going to be a year before it would be upstream, at least.
All right, very well.
Yeah.
Any other questions?
I got it, Phil.
Okay, thanks.
I had two questions related to performance.
Yes.
Can you share any performance comparisons between host to IB versus Phi to IB? And then also, you mentioned that the peer-to-peer bandwidth is limited on some platforms. I'm wondering if you can share some info about that in terms of which platforms and what the magnitude of the difference is in performance?
Oh, I could probably spend a half an hour doing that. Maybe I think what we should do is I could talk to you offline. I mean, I can give you just a couple of numbers. I actually didn't put performance data in this deck because it takes a lot of people to get it approved. But I'll give you some ballpark numbers. On a Xeon to Xeon, with the FDR card, I think our latencies are probably around a microsecond or a little less. On a Xeon Phi card, at the MPI level, maybe it's 5 to 7 microseconds. Bandwidths that is really going to depend on platform. I mean, it's anywhere from 1 gigabyte a second to 1.5 gigabytes a second to over 3, depending on which, or 4, depending on which platform type. So, like I said, I specifically didn't put performance data in here because, first of all, I would have had to get it reviewed by everybody in God at Intel, right? And plus, it's a whole subject that, it depends is the answer to that. It depends on a lot of things. So.
And show some numbers.
Good. DK will actually show some numbers. You'll at least probably share the mic direct. Yes, go ahead.
RDMA CM and IP over IP.
Yes.
Realistic time frames.
Repeat the question.
Yeah, the question was ballpark time frames for when we might see RDMA CM, IP over IP support and things like Lustre. I'm hoping. Oh God, I don't know if I should be saying this. Right now, it's a prototype. Okay, if all goes well, which I can't say, commit to, I would hope by the end of Q3, maybe early Q4, we'd have it in an experimental state, at least where we could start scaling it up at real customer sites. Part of the MPSS. So probably in another 3 to 6 months, we have it somewhat working in our lab now. We have to scale it up, harden it a little bit.
Was that how you envision exports being done from the host and it's NFS RDMA, or we use NFS right now, and so it's performance-wise, we'd like to see
Better.
better.
Yeah, so for NFS performance, right now, the NFS mounts go over this. They have a virtual Ethernet driver that goes between the card and the host, which is not hugely performing. The IP over IP performance that we're seeing right now is also not hugely performant. Again, it's the same problem with code path, slow scalar performance, and going through the TCP/IP stack. We haven't yet started playing with NFS RDMA, but that's also another possibility. We'll probably do some prototyping on that as well. And then, Lustre, which is, directly to the, it's like a direct path to the network, which should be pretty good.
Okay. One more question, Woody, from Samantha.
Hi, and just wanted to ask you, as far as you mentioned the Windows aperture.
Yes.
So who sets it, and what are the sizes? What are the limitations of that?
So the way that they're set is there's this low-level SCIF API, and so he's the one that controls the hardware registers for that. I don't remember exactly how many of those there are. I'd have to get the specifics from that, but the sizes can be big. For example, we're able to map the entire memory space of the Xeon Phi card into the host address space through one of these, and that's 16 gigabytes. So how much address space of the host you could map into the card, I don't know the answer to that. I think I remember something like, there's enough registers to be able to map 16 KNC cards worth of memory, at least 16. So if you want the exact details to that, I can get you in touch with the person that has that information. Yeah.
So the copy proxy mechanism that was used for uDAPL.
Yes.
Why not RDMA for that?
Why not RDMA?
Why not RDMA semantics for that?
Why not use, well, it is RDMA. We use DAPL at the top, so it's RDMA at the DAPL level. Okay, so instead of verbs, level. And the reason for that was because the only way to do this hiding of where the connections are really established with the HCA, you have to control the connection management part of things. DAPL controls the connection management part of things. At the verbs level, you can choose to use RDMA CM, but you can choose to not use it. So we couldn't figure out a way to do the proxying at the verbs level.
Okay. Thank you very much, Woody.
Yep.
Really great. Let's have some coffee, and we'll be back here at 12:30.